Friends, today we are going to learn about C13 NMR spectroscopy. So friends, in my previous lectures, you studied the H1 NMR spectroscopy thoroughly. So few techniques which we used for the simplification of H1 NMR, those things are applied to the C13 NMR also. So if you are following this lecture, I request you to go back my previous lectures of simplification of H1 NMR spectroscopy and observe those lecture or watch those lectures for the better understanding of this lecture. So friends, let's begin with the introduction of C13 NMR spectroscopy. So friends, carbon spectra are used for the determination of non-equivalent carbon in a particular atom. So friends, you can get the direct information about the carbon skeleton of that molecule, which is not observed in the H1 NMR spectroscopy. So in H1 NMR spectroscopy we are observing protons, but in carbon NMR spectroscopy we are directly observing the non-equivalent carbons or simply the carbon skeleton of that molecule. So friends, let's see how difficult is the resolution of carbon 13 NMR, because there are two reasons because of that we have weak resolution or difficulty in the observing C13 nuclei resonance. So first is the natural abundance of carbon 13 is very low. Why carbon 13? Because carbon 13 is the isotope which is NMR active. Okay, it has the odd spin. So friends, carbon 12 is the natural isotope which have highest percentage of natural abundance, but it is NMR active, NMR inactive. So friends, we need carbon 13 isotope which have very low natural abundance, that is only 1.08%. That's why it is very difficult to observe the C13 nuclei resonance. And secondly, the gyromagnetic ratio or magnetogyric ratio of C13 nuclei is very smaller than hydrogen. That's why the excited state and relaxation gives very weak peak in the NMR spectroscopy. Okay, C13 NMR spectroscopy. So these two reasons for which we observe that the C13 NMR is 6000 times weaker than the proton. But now the advanced techniques are there. So one most advanced technique, that is FT-NMR instrumentation, which makes it possible to obtain a routine carbon spectra easily. So what this FT-NMR instrument do, let's see in the next slide. So FT NMR stands for Fourier Transform NMR. So what is meant by Fourier Transform, or what is this technique? This technique, it is a method to collect an NMR spectrum in which a pulse of radio frequency energy is used to excite all the nuclei of a particular isotope. Okay, at the same time we are using pulse. Okay, so that pulse is exciting all the nuclei of particular isotope once at all. Okay, once at all. So friends, in which the all the nuclei in this molecule, for example we are observing C13. So if we have 5 carbons in a one molecule, at the same time all the carbons are excited and relaxed. So what happen after this excitation and relaxation? As the excited nuclei relax, they re-emit ratio wave they emit radio waves of photons which produce an interface pattern called the free induction decay. So this is called as a FID. Okay, this is a FID, free induction decay. And using the Fourier transform, that is a mathematical process called the Fourier transform, computerized program which convert this FID to normal NMR spectra. Okay, so once one at single time we are exciting all the nuclei in the particular molecule to get the FID, and this FID is converted to normal NMR spectra using a mathematical process called Fourier transform. So this is how we are getting the easier regular routine C13 NMR spectra. Okay, now let's see what are the chemical shifts of the carbon 13 uh, spectra. So as you know that, just like H1 NMR, this is also have the range from 0 to 200. Okay, for H1 NMR we observe that the range is 0 to 11, and for the C13 the range is very wide. It is from 0 ppm to 220 ppm. Okay, 0 ppm to 220 ppm. So friends, just for our reference, I will tell you that just multiply the H1 NMR chemical shift by 20, you will get carbon 13. It's a very rough calculation, but most of the time it comes accurate. So just a 20 times higher than the H1 NMR spectra. So similar like H1 NMR spectra, the aliphatic carbons, okay, and now I am talking about the carbons. The aliphatic carbons come around 0 to 40 ppm, okay, 0 to 40 ppm. From 40 to 80 ppm, okay, for 40 to 80 ppm, we have the carbons which are attached to the heteroatom, that is a carbon which is attached to oxygen, chlorine, bromine. They come around 40 to 80 ppm. From 100 to 120, okay, from 100 to 120, from 100 to 120, we have carbon carbon double bond. In between there is a carbon carbon triple bond also, which comes around 80 to 90. Okay, carbon carbon triple bond comes around 80 to 90. And the carbon carbon double bond from olefins as well as from the benzene ring, they come around 100 to 150 ppm. And the most deshielded protons are the carbonyl protons. And you know that there are different carbonyl groups from amides, anhydrides, acids, esters, aldehydes, ketones, etc. They come in between 150 to 220. Okay, they come between 150 to 220. So this is the general correlation chart for the chemical shift of the C13 nuclei. Okay, let's go ahead and let's see it quickly again. The aliphatic carbons come around 88 to or 10 to 60 ppm. The carbons which are attached to heteroatom, they come around 40 to 80 ppm. The alkaline proton come around 90. The carbon carbon double bond from olefins and benzene ring come around 110 to 150. And then ester and acids around 150 to 185, amides around 155 to 185, and then aldehydes and ketones are most deshielded carbons in the C13 NMR spectroscopy. They come around 185 to 220. So these are the general values you need to remind or remember. Friends, there are two types of C13 spectra commonly observed in H1 C13 NMR spectroscopy. So there are, first one is proton coupled C13 spectra and second is proton decoupled C13 spectra. Okay, first one is proton coupled. Now you know that uh, protons and carbons protons and carbons are directly attached in any molecule, and both have the odd spin, or both, if both have the NMR active nuclei, then they can couple to each other. So that kind of spectra is called as proton coupled C13 spectra. And another in which the proton coupling is decoupled using other techniques, and we get the proton decoupled spectra. So let's see the proton coupled spectra. Okay, now first we will see the proton coupled spectra. The spins of the proton attached directly to C13 atoms do interact with the spins of carbon and cause the splitting, okay, according to n plus rule. So H1 and C13 will couple with each other and split into n plus 1 rule. Okay, please split according to n plus 1 rule. Let's see by example. If in the first example we have this C13 and the 3 protons attached to this carbon, then it will show 3 plus 1, that is a quartet. Okay, this carbon will show us quartet. Okay, 4 signals. If we have carbon which is attached to 2 protons, then it will split according to n plus rule, 2 plus 1 3, so it will show triplet. If we have a carbon which is attached to only one proton, then it will split into doublet, and finally if we have quaternary carbon with zero protons, it will going to show us singlet of quaternary carbon. So this is how the proton coupled C13 spectra is observed. Now friends, proton coupled spectra for large molecules are often difficult to interpret. They are very complex due to the multiplets from different carbons commonly overlap because of the C13H coupling constants are larger than the chemical shift difference. Okay, so this all the multiplets overlap on each other, and often we get a complex spectra for the larger molecule. So proton coupled spectra are very difficult to analyze or interpret due to this overlap. So what we do, we use most of the time, majority of the time, we use the second type of spectra, that is a proton decoupled C13 spectra. So majority of the time we see that the C13 NMR spectra is a proton decoupled spectra which shows only singlet because we have decoupled the proton signals. So only singlet can be observed in the proton decoupled spectra. Also friends, C13 and C13 coupling is very rare because it is not possible to have two carbon 13s in a same molecule adjacent to each other. So friends, carbon 13 and carbon 13, that is a homonuclear coupling, is not observed in the C13 NMR spectra. So friends, we get only singlets. Okay, only singlets. So this proton decoupled spectra is of same molecule as we saw in previous. Okay. Okay. So this proton coupled spectra is now decoupled, and you can see that you have clear signals of all the carbons. So as we already studied, the aliphatic carbon comes around 20 to 40. The carbons which are attached to the carbonyl comes around 40. The carbons which are directly attached to the heteroatom comes around 40 to 80. Aromatic protons or carbon-carbon double bond proton carbon-carbon double bond containing carbons comes around 120 to 150, and the carbonyl comes around 150 to 200. So this is how we observe the proton decoupled spectra. Friends, there are many techniques used for the simplification of this complex spectra, or I will say decoupling technique. So there are proton or a noise decoupling technique, off resonance decoupling, and DEPT. So friends, we have these three techniques we already studied in the simplification of H1 spectra. So please watch those videos of simplification of H1 spectra. In the next video we are going to learn other two techniques, that is off resonance decoupling and DEPT. Thank you very much. If you have any doubt, feel free to ask me. Thank you.